In this tutorial, we're going to look at the alkali metals. The first aim is to describe the shared properties of the group 1 alkali metals, then compare the reactions of the alkali metals in water, and finally explain why the alkali metals become more reactive down the group. Now, if I told you a material was as soft as butter and could be cut like butter, it broke down and dissolved in water, it turned black when exposed to air, and was highly explosive when put in water, I imagine you would not be thinking of a metal. But the alkali metals do just that. They're a very unique group of metals. So you find the alkali metals in group 1 on the left-hand side of your periodic table. They are lithium, sodium, potassium, rubidium, cesium, and francium. Most exam questions are centered around lithium, sodium, and potassium. All alkali metals share the following properties. They are all soft, like butter. They're all highly reactive. They have a very low density. Normally metals are quite dense materials, but not the alkali metals, very low density. In fact, they all float on water. They are all explosive in water. They have to be stored in oil, otherwise they'll react with the atmosphere and form an oxide layer and turn black. And they all have a low melting point. Again, not common in metals. Make sure you take note of these shared properties. Most importantly, you must understand the reactions between alkali metals and water. Whenever you react alkali metals with water, you get, well, obviously the alkali metal, which is a solid, and you react it with water, which is a liquid, and you'll form every time a metal hydroxide, which is aqueous, and hydrogen gas, which is gas. Now, metal hydroxides are alkali substances. This is why they're called the alkali metals. When they react with water, they produce an alkali substance, kind of the opposite of an acid. But this hydroxide dissolves in the water and forms an aqueous solution. So if you have to write the word equation for a specific alkali metal, you just need to replace the word metal with the metal you choose from your list. So, for example, lithium plus water. You wouldn't actually need to write metal there, just lithium plus water produces lithium hydroxide and hydrogen. Whereas if you picked potassium, you just replace it with potassium. So potassium plus water makes potassium hydroxide and hydrogen. This applies for any alkali metal you choose from this list. If you have to write the balance symbol equation, there's a really easy way to remember it. Well, firstly, you have to get the chemicals right. So lithium is Li, you can find that on your periodic table. Water, you should know by now, is H2O. Lithium hydroxide, well, you have Li for lithium, and hydroxide is always OH. And hydrogen gas is H2. Remember the 2 there. You don't get hydrogen gas as a single atom. There are always 2 atoms of hydrogen bonded together to make a diatomic 2-atom molecule. So once you know that, all you need to remember is 2, 2, 2, and you'll get the balanced equation. 2 lithium plus 2 water molecules produce 2 molecules of lithium hydroxide and hydrogen. Notice that the small 2 is here for hydrogen. You do not put a big 2 there. You could obviously work this out the proper way and do a proper balanced equation, but this is a shortcut. Just remember 2, 2, 2 for alkali metal. Let's take a different alkali metal. Let's look at rubidium. All I've done is replace Li with Rb for rubidium. Everything else is the same, except for here, rubidium hydroxide instead of lithium hydroxide. Once again, 2, 2, 2. You can apply these rules to any alkali metal. So it could be potassium produces potassium hydroxide, or you could choose cesium, produces cesium hydroxide. So that is how you describe the shared properties of the group 1 alkali metals. So the most important part of this tutorial is comparing the alkali metal reactions in water. This is divided into 2 parts. Firstly, you have to be able to observe well, so you have to say what you see. And then secondly, at a higher level, you have to explain the reasons for what you see, what you observe. So the first metal we're going to look at is lithium. The first thing I do is add universal indicator to water. You'll notice how the indicator turns green, indicating the water is neutral. Now, here's a piece of lithium. Notice how the lithium is covered in a fluid. That fluid is not water, it is actually oil. All alkali metals must be stored in oil to stop them reacting with the air. You can see the top of lithium is black. That's an oxide layer that's formed as lithium quickly reacts with the oxygen in the atmosphere, forming this black layer. So you can see that here as I move it closer to the camera. But notice what happens when I cut lithium. You still get a nice shiny metal, as you might expect, so it hasn't reacted with oxygen yet inside. Notice how it floats in oil. So here's the first observation I want you to make note of. It floats on oil. That means lithium has a very low density. Remember, oil floats on water and lithium actually floats on oil, so it has a very low density. It's the least dense of the alkali metals. So now let's watch the reaction. You can see as I drop lithium in, it starts to fizz. It starts to move around. So let's see what's going on. Well, firstly, you can see it floats on water, obviously, because it has a very low density. You can see it starts to fizz, and that's because hydrogen gas is being produced, just like I showed you in the equation on the other page. You'll also notice that the universal indicator is turning purple. That indicates that a hydroxide is being produced. In this case, it's lithium hydroxide being produced, and I said it's an alkali. Universal indicator will change green from a neutral substance to purple when they detect alkalis. Next up, we're going to look at sodium. Watch carefully. So you can see sodium actually sinks to the bottom of oil. So it is stored in oil, but it's more dense than lithium. You can see it cuts really easily, almost like soft toffee. And inside, nice shiny metal. Now we drop it in again. Look what happens. This time it's moving around more. More gas is being produced. It's more visible. You may also realise that it forms a pearl-like ball as it skates on top. That's because it's melting. So, sodium floats on water, and the explanation for that is because it has a very low density. It fizzes just like lithium because it produces hydrogen gas, but it produces more hydrogen gas, which is why it's more visible. It melts on top of the water, so the heat generated by the reaction melts sodium. The explanation for this must be sodium has a low melting point. And also, universal indicator turns purple, so this time sodium hydroxide is being produced. That's the alkali substance which dissolves in the water to form aqueous sodium hydroxide. So now let's look at potassium. Potassium is more dense than lithium, so sinks to the bottom of oil, but will still float on water. It's softer than lithium and sodium and cuts really easily, more reactive. Look how black it is. It's formed an oxide layer very quickly. And if we put it in water, it reacts more vigorously. It's far more reactive than sodium and lithium. Watch. So it's on top, it catches fire, produces lots of hydrogen gas. So let's just take note of the key observations. It floated on water because it had a very low density, fizzing because it produced hydrogen gas, lots more of it this time. It melts because it has a low melting point, just like sodium. But this time it actually caught fire. Why? Because so much heat was produced and so much hydrogen gas was produced that the heat caused the hydrogen gas to ignite, to catch fire. You couldn't see it very clearly from the video, but the flame is a lilac colour. It's a purple lilac flame. You must say lilac flame. It's a very popular point they raise in exams. And also turns the universal indicator purple, so that must mean potassium hydroxide is being produced. You can test for hydrogen using the squeaky pop test. So I'm collecting it in some water. So I've held metal, it's producing hydrogen, displacing water. So now I've got pure hydrogen in there. And if I put a lit splint, you get a squeaky pop sort of test. Probably not the best squeaky pop there, but you get the point. Be aware that if an exam asks you to say what you see during a reaction, these are the kind of things you have to write. You're not explaining, you're just literally saying what you see. If you have to explain what you see, then you must say what you see and give a reason for it. For example, why does sodium form a molten ball and float on water? Well, why does it do that? It floats on water because it has a very low density. It forms a molten, a melted ball of metal because it has a low melting point. And that is how you compare the reactions of the alkali metals in water. Finally, we have to explain the pattern of reactivity with the alkali metals. Lithium is the least reactive and francium is the most reactive. They increase in reactivity as you go down the group. Now make no mistake, they're all very reactive metals, but as the atomic number increases from 3 to 11 to 19, 37, 55, 87, they increase in reactivity. We can only test these in a lab because it gets too dangerous after this point, but you're more than welcome to find these online. There are YouTube footage of francium reacting, but those are fake. And that's because francium is so reactive that it's almost impossible to separate it from whatever it's bonded to. So the key to answering this question is understanding that as you go down the group, the elements gain more shells. Now firstly, think about how alkali metals react. All alkali metals in group 1 have one electron on their outer shell. They become stable by losing that outer electron. Now, remember that electrons have a negative charge and the nucleus, because of the protons packed inside, have a positive charge. Opposites attract. So let's say we've got a nearby atom that wants to steal that electron away from lithium. Well, as it gets close, you can see there's an electrostatic force here. Positive nucleus here is trying to steal the electron away from this positive nucleus. Because there are few shells separating this nucleus from the outer electron, there's a fairly strong force of attraction holding them together. So it's harder for the electron to separate off, but it will. But if we look at sodium, you can see there are more shells. In other words, there's a greater distance between the positively charged nucleus and the outer electron. Therefore, there's a weaker force of attraction. A bit like holding a north pole and south pole of a magnet, the further away they are from each other, the weaker the magnetic force of attraction between them. So this time it's easier for this atom to take the other electron because there's a weaker force of attraction between the protons and the outer electron. So it basically leaves more readily. And now you just play this logic forward. So potassium has more shells. There's a greater distance between the positively charged nucleus and the outer negative electron. So there's a weaker force of attraction, so it's much easier for potassium to lose its outer electron and react. So remember, the answer is because as you go down the group, the atoms have more shells. This means there's a weaker force of attraction between the positively charged nucleus and the outer electron, so it's easier to lose that outer electron. And that is how you explain why the alkali metals become more reactive down the group.